Good morning, ladies and gentlemen. I hope you guys are all doing well today. Welcome to this beautiful, fine Monday morning. So today, what we're going to be looking at is we're going to be looking at two pieces of info in this particular video lesson. We're going to be looking at nuclear terms and notation and some different categories of nuclear reactions. So because this is there's some pretty new stuff for you guys in this particular section. I've posted a bunch of articles along with this video on Google Classroom to help explain in some more detail some of the really cool things about some of the new subatomic particles we're going to be talking about today. Yes, there's a lot more than protons, neutrons, and electrons in existence. I know, right? Bad. Okay. So, ladies and gentlemen, the nuclear notation and some of the nuclear terms you will have seen before, but it was a long time ago back in grade 10. And I know when I teach grade 10, I only spend a little bit of time with it because it doesn't show up again until now. All right, so don't feel bad or guilty or anything if you don't remember this. So, as you know, ladies and gentlemen, protons, positively charged particles found in the nucleus of the atom. That part I hope you'll remember. And as you know, remember from chemistry, the number of protons determines the element type. So that, I hope you guys remember that as well from chem. So in a neutral atom, so something that is not an ion, you have the number of protons is equal to the number of electrons. Okay? So, ladies and gentlemen, back to chem, when you lose electrons in a redox reaction or an ionizing reaction, you wind up with a positive charge when you lose them or a negative charge when you gain them. Okay, so ladies and gentlemen, this part might be new. The atomic number, or the number of protons, is represented by the letter Z. Why it's Z, I couldn't tell you. In all honesty, I have no idea. Remember neutrons, you guys remember, they are neutral particles found in the nucleus. And the neutron number is labeled as N. Now, the number of neutrons is going to vary from atom to atom, forming what is called isotopes. Okay, isotopes don't get talked about a ton. I think we talk about them a bit in Science 10, talking about a bit in Chem. They kind of dance around a little bit through the course, but we're going to talk a decent amount about them now. They also show up in Science 30, so if you guys have taken Science 30, I know we've talked about isotopes then too. All right, so atomic mass of the atomic number. This you should absolutely remember from chemistry. It is the total number of protons and neutrons in the atom. Okay, and protons and neutrons have the greatest mass component of the of an atom. So I'm going to pause the video for a sec. I'm going to run and raid my fridge and be back with some apples. I'll be right back. All right, I'm back. So I've raided my fridge and pulled out what fruit is left in the house. I need to get groceries. So in here I've got a plastic bag which has a hole in it and a couple of apples, an orange, and a banana. So when we think about this, I always like to use this fruit analogy to talk about the subatomic particles and their relative mass. So with this, the bag of fruit here and the plastic bag, well, both of them have mass. Both are made of particles. And they both take up space. They both, So ladies and gentlemen, what is relevant though? If I was to take this bag of fruit and put it on my kitchen scale, is the fruit going to make up the most of the mass, or is the plastic bag the fruit, right? The plastic bag has mass, but its mass is so irrelevant in comparison to the rest of the fruit. It is what is called negligible. Okay, so the same with electrons. Electrons, their mass is negligible. Their mass is irrelevant in comparison to the protons and neutrons. So you can think of the mass of the plastic bag being and of the equivalent to the mass of electrons, and the mass of the fruit inside the bag equal to, or analogous to, the mass of the protons and the neutrons. Okay? All right, I need to buy fruit when I get groceries. That banana is looking a little bit sad. It's almost in banana bread category. Okay, I should make banana bread. All right, so ladies and gentlemen, That's our analogy. So nucleons is a term for protons and neutrons combined. Okay. And the atomic mass is often indicated as a number attached to the back of an element name. Okay. So that comes up fairly common, ladies and gentlemen. So if we have something that is carbon-14, say, that is the sum of all of the nucleons. Okay. Sounds good? Okay. Well, where can we get the number of protons? Periodic table. So, ladies and gentlemen, there's a very good reason why on your data sheets there is a periodic table. Okay. So, here it is. This is the Physics 30 variety of the periodic table, not nearly as detailed as the Chem 30 periodic table. But it has the information that you need for it. So, for example, carbon, you can find carbon here. Now, where am I going to get my proton number? The number 6. That number 6 is the atomic number, and the atomic number is how many protons are in that atom. I really hope you guys remember that from Chem. Okay. Chem is fun. I love teaching Chem. Well, I don't think there's no science I dislike teaching. Science is just fun. Okay, so ladies and gentlemen, isotopes, another really important definition to keep in mind here. Now, an isotope is something that have the same number of protons, the same element, because the number of protons that determines the identity of the element, but they have different numbers of neutrons. So carbon-12, carbon-13, and carbon-14, say. Well, all of them, each of them has 6 protons. Okay, so it's all carbon. However, the number of neutrons is different. Now, I like carbon-14. Carbon-12 is the most common variety of carbon. Carbon-14 is cool. Everyone has a little teeny bit of it. And carbon-14 is radioactive, and it is used in archaeology for dating the age of any artifact that is made of something that was once living. Isn't that cool? I think it's cool. So something else to keep in mind as well, I know this is something that was discussed back in probably Science 10, but let's go back to carbon. So I want you guys to find our atomic mass, our molar mass. You guys see that there with carbon? Okay. So carbon is 12.01. Now, what is that 12.01? That is the average atomic mass. So that means only of that 0.01, that's the only bit that is contributed to that 12 of these guys. So carbon-12 is incredibly common, but these guys are not common. And carbon-13 is more common than carbon-14. Cool, hey? That's where all of those atomic numbers come from, the average of the atomic mass. And it works out to be the same as the molar mass. Chem is awesome. Physics is awesome. So, ladies and gentlemen, their nuclear notation is how we write out this information. So, X is the element symbol, okay? And then A and Z. You can also write it out as X, A, Z. I will write it out as either. I'm not particularly fussed about which one you write it out as. It just depends on, I guess, how I feel that day, whether I write it like this or like this. Doesn't matter. But that X, ladies and gentlemen, I'm actually going to write this out properly on the side here. So the X is your element symbol. Okay, that you get from the periodic table. And A is the atomic number. So, which you also get from your periodic table, and that indicates our number of protons. And Z is equal to, I wrote this backwards, it's Monday. And it actually is Monday. Happy June 1st, ladies and gentlemen. There we go. So A is equal to our mass number, which is equal to protons plus neutrons. So remember, ladies and gentlemen, that electrons aren't counted in the mass number. So the mass number is often used as instead of like kilograms, because that's not overly helpful. The mass number is representative of the sum of the protons and of the neutrons. And electrons are negligible in the mass. So Z, ladies and gentlemen, that one is our atomic number. And that is the number of protons. All right. So your example, ladies and gentlemen. So if we have carbon, well, carbon has 6 protons. And if we're going to say carbon 12, it will have 6 protons and 6 neutrons. Okay. So how we can determine that is our atomic mass, so A, is equal to our lovely value of N, being N the number of neutrons, plus Z. Okay? So if you ever need to figure out, well, how many neutrons are in a substance, this is what you would use. So your neutrons are equal to your atomic number minus the number of protons. Okay? So I'm sure you guys remember doing that back in Science 10. It's not super new. It's just been a while. Okay. Science 10, long time ago. Like, do you guys remember when EK equals 1/2 mv squared and rearranging that to get V was hard? And you remember that? And nowadays, it's just something that you do. Isn't that awesome? I love seeing it. I love seeing that. You guys start at grade 10 and then go to grade 12 and see how much you guys have learned. I always love that. All right. So ladies and gentlemen, how many neutrons are contained in a gold nucleus? All right. Well, ladies and gentlemen, the atomic mass of this particular gold nucleus is 197. So that's the total number of neutrons and protons. Z is the number of protons, which is 79. And the number of neutrons, as we rearranged right there, is equal to A minus Z. So that would mean our 197 minus 79 is going to give you the lovely value of 118 neutrons. Okay. Now, in this case, ladies and gentlemen, I don't want you rounding these numbers to significant digits. These are absolute values. There's no partial, there's no rounding. If you have 79 neutrons, you have 79 neutrons. If you have 118 neutrons, there's 118 neutrons. That's the way it is. So I know I've been harping on sig digs for how many years now, but these are absolute values. There's no rounding. I do not want to see 1.2 times 10 to the power of 2 neutrons because that's rounded. These are exact numbers here. Sounds good? Okay. So, question number 2. How do the nuclei of these 3 atoms different? How are they the same? Well, how they differ, ladies and gentlemen, they differ based on the number of neutrons. Okay? Because look at these values up here. The mass number is different. Okay? But because they are the same number of protons, they are the same atom there. Not the same atom, the same element. So because they're the same element, their mass is different. They are isotopes of each other, which means they have a different number of neutrons. I'm having a hard time not writing on my face. There we go. And the same number of protons. So therefore, they are the same element. Sounds good, guys? Cool beans. All right. So, ladies and gentlemen, any questions so far? We're on a video. If you have questions, email me or sign up on Google Classroom for video chat help on Google Meet. All right. So, ladies and gentlemen, we've got, this is a good time for you guys to pause and go get some tea, as we're going to be switching topics here. All right, now that you're back and you have tea, we're back, okay? We're going to be looking at a few different categories of nuclear reactions. We're not going to be looking at all of the categories. We've got a different lesson for nuclear fission and nuclear fusion. Those are some of the more really practical nuclear reactions. Nuclear fission is what you see in the CANDU nuclear power plants. Okay, Canadian tech. It's pretty cool. All right. So this is the part of the video where you're going to be seeing stuff that you may not have seen before. We're going to be talking about some of the subatomic particles that we haven't talked about in science in high school, that are not in the high school science curriculum until now. And we're also going to be talking about matter and antimatter as well. This is where I've got some of the articles on Google Classroom to kind of explain a little bit more about that if you are curious beyond the scope of this video. All right. So, ladies and gentlemen, a nuclear reaction. This is a reaction where one element is converted into another. Now, remember back in the day, we're talking about ions and how your teacher hounded on you can, protons and neutrons, they never change. Protons always stay the same, and the electrons involved in the chemical reactions, electrons can leave and go, but no protons and neutrons. Well, welcome now. Protons are now leaving. Okay, so are electrons, and we are also having like subatomic particles converting one into the other. Like, it's insane. So with these nuclear reactions, they can sometimes be called a transmutation or a nuclear or radioactive decay. So that's our more of our focus today is more on the decay reactions, and fission and fusion are going to come in a couple videos later. So what happens essentially is that nucleus in a radioactive element is unstable for whatever reason. And thought that this instability comes from there just being way too many protons all jammed into a nucleus, because the bigger the nucleus, the more likely it is to be radioactive. And even it could be the number, and sometimes the number of neutrons. So when you have too many neutrons, like carbon-14, it comes from having more neutrons. It somehow changes the stability of that nucleus. And when it's unstable, it falls apart and is trying to seek a lower energy element, okay, a more stable nucleus. So this parent element is the original or initial element in the reaction. The daughter element or elements are the ones produced in the reaction. Okay. Now, this is really different from a chemical reaction, like completely different. In a chemical reaction, our atoms are just rearranging themselves. Electrons may or may not be transferred, but, okay, the carbon's going to hang out over here, and then he's just going to swap with another atom, and okay, all's good. But the number of protons isn't changing. So when we look at our chemical reaction here, we've got a combustion of octane. So you guys like this reaction? If you enjoy driving vehicles with an internal combustion engine. So whereas notice, well, we got carbon here, and oh, hey, look, there's carbon here. We got 16 carbons here. We got 16 carbons here. So this guy is absolutely a chemical reaction. Whereas when we have this, we've got the same atoms, the same elements on both sides. They're just rearranged. Okay, there's even the same number of them. Whereas we come over here, ladies and gentlemen, with this nuclear reaction, is that, well, we've got carbon and helium. Well, now we've got oxygen and a neutron. Well, where'd the carbon go? Where'd the helium go? I want you guys to guess what happened to them. What happened in this case? Look at the numbers. They fused. This is an example of nuclear fusion. We can't do this on Earth, by the way. So, as far as we know, only stars can do this. Yeah, pretty cool. So here, ladies and gentlemen, we've got carbon and helium. Well, look at this. Number of protons, 8. 8 protons. They've just combined. Look at the mass numbers. We got 17. We got a total of 16. So the law of conservation of mass still applies. It's just now, we're now looking more at it at the nuclear level, at the level of the nucleus. Okay? So here we have our carbon and helium. They are being converted into oxygen. Sounds good? Awesome. All right. I couldn't find the mouse. There we go. So, ladies and gentlemen, there's a ton of different types of nuclear reactions. We're going to look at some of them. And however, all nuclear reactions are governed by the principle of conservation of charge and conservation of mass and nucleons. Okay. So, ladies and gentlemen, these are principles 7 and 8. So if you get any questions about that, you would find those right back there on your list. All right. So if we had a diploma, that's where you'd find those. All right. So we're going to kind of work through some of these principles and we'll talk about it. So, ladies and gentlemen, uranium-325 nucleus absorbs a neutron and then splits into bromine 87 and 3 neutrons and 1 other daughter element. What is the unknown daughter element produced by this reaction? Okay, well, let's start by writing out what we've got here. So we have uranium-235. Now, what do we put down at the bottom here? 92. Where did I get that 92? Periodic table. What is the significance of it? Number of protons. So, pull out your periodic tables. You have to have your periodic tables out with this. Your periodic tables should be in the data booklet that I gave you. Okay? Or pull one out from chemistry. It's all going to be the same. And then you find that just by looking for uranium, which is right there. Okay. I see you. Got it? Yeah. Found uranium. I found you. I can't help it. All right. And it absorbs a neutron. Now, for the symbols for these guys, for your subatomic particles, ladies and gentlemen, they are right. Where'd it go? That's weird. They didn't give them to you. Strange. Okay. I didn't put them on there. It's weird. I thought they did. So, memorize this one. N is our neutron. Now, how many protons do we have in a single neutron? 0. How many nucleons do we have in just one neutron? 1. So this is the symbol for a neutron. So what I would do is just pause the video and write this down on your data sheet and label that as this is the symbol for a neutron. Sounds good? All right. So these guys, so when we throw a neutron at this guy, this is going to break into elements. And this, ladies and gentlemen, this reaction releases a mountain of energy. And it is this general reaction that is used in nuclear reactors and has been used in some of the atomic weapons as well. Okay. So, ladies and gentlemen, bromine 87. Bromine with a mass number of 87. Remember, that's our mass number, the number of nucleons. And, well, what's down here? Where do I get it? 35, and that comes from your periodic table. Okay, and it produces 3 neutrons. So our coefficient of 3, that doesn't change. And with a mass of 1, I should make my ends actually consistent. Okay, so 3 neutrons. Okay, and it's going to release an unknown element. So we've got X, A, and Z. So this is where we're going to be using the conservation of charge and the conservation of mass/nucleons. Okay. Now, as for this one, we're going to be using this guy here. Okay, so let's start with our protons. Let's do that. Let's do the conservation of charge first. So the conservation of charge / conservation of nucleons means the charge on each side is going to have to be the same, and the number of nucleons is going to be the same. So in this case, I've got 92 protons here and none here. So I'm going to use blue to represent my protons. So for my protons on this side of the arrow, I have a total of 92. That means on this side of the arrow, I have to have a total of 92. Okay, so, but I have 35 with the bromine, plus 0 here, plus this value of Z. Well, how do I get this? Now, what's the total number of protons have to be? That's a Z, not a 2, okay, guys? Well, that has to equal 92. So I'm going to rearrange this and have 92 minus 35, and that's going to give me the total number of protons that are on Z. So that's going to equal Z, and once you do the math, you get a lovely value of Z of 57. Okay, well, the nice thing about that is that now tells us what X is. Okay, so I'm going to go find out what X is right now. You're going to go to your periodic table, and you're going to look for your atomic number of 92, which you then, 92, a 57, beg pardon, and once you go and find 57, it's right there. Okay, so lithium. Okay, so now, ladies and gentlemen, I'm going to switch colors here and we'll go green. Why not? Now we're going to look at our mass number. So our total mass number, which is going to be our total of all nucleons, well, 35 plus 1, well, that's 235. Goodness, 235 plus 1 is 236. So what that tells us is we need to have a total number for our A value over here. Okay, so that's equal to the total A. So we're trying to find our total A, this guy right up there. Okay, so it has to be a total sum of 236. Okay, so, well, 236, we've got 87. So the same way we did up here. So 236 minus 87. Now watch this. See that? 3 times 1. The same way you would do in any other balanced chemical equation. All right. So you're going to then be minusing 3 for those neutrons. And then that is going to give you the value of A. Okay. So the value of A up here, ladies and gentlemen, is going to be 146. So we can get our final answer now in pink, because why not? Colors are fun. As we have X is La, the element symbol from the periodic table. A is 146, and Z is 57. All right. Sound pretty good? All right. So this particular reaction is an example in a nuclear fission reaction, but the principle is going to be the same in any of the nuclear reactions. So of the ones that we're going to be looking at today, and we're going to be looking at 3 types of what are called 3 types of radiation: alpha radiation, beta radiation, and gamma radiation. Okay, so we'll look at fission and fusion later. Okay, now most of these are, the ones we're going to be looking at are going to be from decay. Now when we're talking about radioactive decay, that's when a radioactive element is going to break down. Okay, it happens naturally. These nuclei are unstable, and then they will start flinging off radiation to attempt to become stable. And we'll talk a bit more about that end when we talk about half-life. Okay, so ladies and gentlemen, an alpha particle is a helium nucleus. Okay, I am going to rewrite this so we say, I don't like that, Adam. I want to say nucleus because there's no electrons there. Okay, so this one you've seen on your data sheet. We've talked about it before. So we'll have an A and then a 4 and a 2. So 2 neutrons and 2 protons. You may also see it as written like this. Okay, you might also see it written with these guys on the other side. It doesn't really matter. Okay, now to produce or release an alpha particle, the parent obviously has to have enough protons and neutrons to actually release and let go of 2 protons and neutrons. So helium can't go through alpha decay. All right. So, ladies and gentlemen, let's write out the overall equation for this. I'll write this letters on this side just to shake things up. Okay, so whatever element this is going to go through, it is going to release an alpha particle. Okay, well, in this new element, just because I can, we're going to call it Y. And the thing is that Y's A value is going to be this A minus 4, and its Z value is going to be Z minus 2. So that is your overarching equation for alpha decay. So when a radioactive element is going to start flinging alpha particles. Okay? So when you're going to see a question like this, write out the equation for the alpha decay of uranium-238. So you're going to pull out your periodic table, and you're going to see from your periodic table that your atomic number for uranium is 92. And the 238 is the mass number, which comes right there. That's given to you. And alpha decay, well, you need to know that that means that this guy is going to start breaking down and flinging off alpha particles. We also make the assumption that we're going to fling out 1 alpha particle per nucleus. Okay, so he's going to fling out an alpha particle. He's going to throw away a helium nucleus. Okay, and I don't care if you write it like this or write this. Potato, doesn't matter. Well, now we need to figure out what this guy is. So our XAZ. Well, 238 minus 4 is equal to 234. So I'm just going to write this like this. Okay. That's supposed to be a 4. Let's make this legible for you. That might help just slightly. Okay, well, Z here, 92 minus 2, well, that's going to give you 90. Okay, well, ladies and gentlemen, what's X? Go to your periodic table and find the element number 90 on the periodic table, and you're going to find, ladies and gentlemen, TH. If I remember correctly off the top of my head, TH is thorium. I don't remember his name. Yeah, thorium. I was right. Named after God of Thunder. Okay, from Norse mythology. If you guys get a chance, read some Norse mythology. It's actually really, really funny. Yeah, I think my favorite, the silliest story of them that at least what I find the silliest, is the one where the Asgardians, they hire an ice giant to build a wall for them, and they're actually really rude about it. They're complete, just disrespectful guys towards this ice giant. But it's really silly, though, especially how Loki fools the ice giant. That part's funny. Give it a read. It's hilarious. Okay, definitely worth reading. Okay, so ladies and gentlemen, beta radiation. Okay, this, ladies and gentlemen, is where we're going to have some new subatomic particles here to talk about. Now, in beta radiation, what happens is a neutron is going to change itself. It's going to be transformed into a proton. And while this happens, it's going to emit an electron and a diminutive teeny tiny particle called an antineutrino. Okay? All right. This is where the conservation of charge comes in. So we'll notice if a proton is or a neutron, which is neutral, is going to be converted into a proton, it's also going to be converted into an electron. So that this neutron becomes a proton and an electron. Exactly how that happens, that is beyond my level of education. So I sadly cannot answer that question for you. And so therefore, your conservation of charge is maintained. Okay, and the conservation of nucleons is, because we've gone from a neutron to a proton. So we have the same number of nucleons, but the nucleon's identity is now different. Okay, so let's talk about this antineutrino. I'm going to pause here for a little sec, and we're going to talk a little bit about neutrinos and antineutrinos, and we're going to talk a little bit about antimatter. Antimatter is not just a science fiction thing. It's not just a thing that shows up in, what's the author's name? It shows up in the book, Angels and Demons. It's a good book. The same guy who wrote the Da Vinci Code. I can't remember the name of the author. Anyway, they talk about antimatter in Angels and Demons, and it's rather ridiculous, but in how they do it, science is not there, but it's an entertaining book. And antimatter is not very common. It does exist in nature, but we don't find it very easily on Earth. The most common place is going to be created through stars and cosmic rays are going to have some antimatter. But what antimatter is like an antiproton, for example, has the same mass, the same size, but the opposite charge. So an antiproton has a negative charge but the same mass. A positron is the antimatter to an electron. It's the same mass, but it is positive in charge. A neutrino and an antineutrino. Now, they're both neutral, but I actually have a whole article on neutrinos and antineutrinos and what the difference is between them on a couple different articles on neutrinos, antineutrinos, and antimatter on Google Classroom. So if you guys want to read those, if that's going to be interesting for you. But the neutrinos and antineutrinos are made of other subatomic particles. Remind me, correct? I think they're called leptons, and they just have different types of leptons or opposite types of leptons. So the sum of all the leptons winds up being neutral, but they just have opposite types. So because they have opposite types of leptons, there's neutrinos and antineutrinos. Now, when matter, so say a positron and an electron, so matter and antimatter, are going to collide, they're going to annihilate. Okay, they're going to disappear. They are going to completely disappear into a fiery ball of radiation and energy and light and what have you. So the reason why matter can exist and we don't just have like annihilation of matter going on all the time is because there's a ton of protons, neutrons, and electrons. But antimatter itself is very, very rare. And the cosmic rays that come flying to the Earth from the sun are dealt with by our atmosphere. Okay, so any antimatter there is dealt with by the atmosphere. Okay, so ladies and gentlemen, I hope that information about matter and antimatter is helpful to you. If you want more information than that, check out the articles on Google Classroom that I've linked there for you. Okay, they're actually really interesting. All right, so ladies and gentlemen, an electron comes out in what is called beta negative decay. Okay, and an electron, no significant mass when compared to the proton or the neutron. All right. Okay. So, ladies and gentlemen, how we write out an electron is B0 -1 for beta decay, or I often write it like this because it's an electron. Okay, sometimes I write it like that, but this is the better way to write it for radiation. So write out the B negative decay for lead 212. Well, lead, Pb, the Pb in lead is for Latin, and it's plumbum. And that came from plumbing because the Romans used lead pipes to pipe in their water. So they didn't realize lead was toxic, but that's where Pb comes from, plumbum. So the Romans using lead for plumbing. Anyway, random history. So 212, and when you get off your data sheet, 82 is the atomic number. Well, we are going to be releasing a beta particle. Okay, no significant mass. Okay, no nucleons, charge of -1. Okay, now that the -1 is going, by using this -1 protons, is going to help keep our, oh goodness, Mike, can you hear my email? It's just dinging like crazy. It's going to help keep our conservation of charge. Okay, so that's why we use this symbol there. And it's going to release an antineutrino. Okay. And then we need to figure out, well, what is left? Okay. Well, 212 minus 0 is 212. Okay, well, that's not too shabby. All right. Well, let's look at this guy. 82 and -1. Well, we have 82 on this side here. And what -1 is going to give us 82? 83. Okay, so the mass is the same as we talked about earlier. However, that number of protons is changing. A neutron is converted into a proton. Okay, all right. So 212 nucleons on one side and 82 protons. And, or you should say the charge, beg pardon, 82 protons, so positive 82, positive 82. Sounds good? All right, that's how you check your work for that one. Well, you solved it, actually. All right, so now we're on to our beta positive decay. Now remember how I talked about antimatter? In this case, we have a proton in the nucleus is going to be transformed into a neutron. Okay, so a proton goes into a neutron. Now, what this is going to give us is a positron and a neutrino. Okay, a positron, its symbol is E positive. This is the antimatter or antiparticle to an electron. So remember how we talked about they have the same size and the same mass, but the opposite charge. And when they collide, kaboof, they disappear in a flash of gamma radiation, light, energy, what have you. Okay. So, and a positron, beta positive, that's its symbol. Okay, or E positive. It has no significant mass, like compared with a neutron and a proton. So same idea as an electron. And a neutrino, once again, extremely small neutral particle, and it's antimatter to the antineutrino. So remember, as I mentioned earlier, even though they're neutral, the little tiny leptons that they're made of are just the opposite types of leptons. Okay, and honestly, guys, neutrons and protons and electrons, they're also made up of smaller particles too. I know, right? It's insane. It's insane. Nuclear physics is crazy. It's cool though. All right. So, ladies and gentlemen, we have what isotope will beta positive decay of a thallium-202 produce? Okay, well, we've got a TL and 202 from the question, and from your data sheet, 81 for thallium. And it's going to decay to produce a beta positive particle, so a positron. Okay, let's actually write this up here. I want to write this. So we have a proton is going to be converted into a neutron. It's going to be converted into as well a positron, 0 plus 1. Okay, so this plus 1 here is going to maintain that conservation of charge there, and your conservation of nucleons, and there is our neutrino. Okay, so just a V. Antineutrino has a line on top, neutrino has a V. Okay, so for this guy, he's going to, oops, I am writing things down. There we go. It's Monday, and it truly is Monday. Okay, so we're going to get ourselves a positron, some antimatter. We're going to have a neutrino, and then we're going to have our unknown element here. Well, 202 and 0, 0, well, A is going to be 202, using our conservation of mass. All right, 81. We have to have a total of 81 protons. So we come over here, ladies and gentlemen, well, 81 and plus 1. Well, what plus 1 gives me 81? 80. Okay, so that's 80. Well, what, according to our periodic table, ladies and gentlemen, has 80 protons? Mercury! And the element, not Freddie. Freddie Mercury, Queen, great band. Gotta love Queen. Okay. So, ladies and gentlemen, when you're showing your work on the assignment, this is good enough. If I say write the reaction for this, just write that. You don't have to show me anything else. That's fine. Okay? All right. There might be more marks involved than 1 point for writing it out. I haven't decided yet. Okay. All right. So, ladies and gentlemen, gamma radiation. So for this one, most of these types of nuclear radiations, they're going to be accompanied by a gamma ray. Now, recall gamma radiation from our unit on EMR. It's essentially just a high-energy photon, okay? And it's some energy, high-energy photon. It is, and with gamma radiation, it's not a nuclear transmutation by itself. One element isn't being released or converted. It's just releasing some energy, okay? So you can have carbon-12, if it's going to go through just gamma decay, well, nothing's changing. You just get your gamma radiation. I have a terrible time drawing this. It's like some curly QY. Okay. So, however, a lot of reactions are also going to include gamma radiation in their nuclear decay. Alrighty-o. So, ladies and gentlemen, we've got some practice problems here for you from your workbooks. So give those a shot. And I've also got another practice problem here for you guys. And this one is actually bringing us right back to your second unit, actually. It's going to be your hint there. All right. So, ladies and gentlemen, I hope that you guys enjoyed the video. Check out those articles that I have linked on Google Classroom to accompany this lesson. And have a good day. No fires, injuries, or explosions. All right. See you guys later. And now, as usual, I can't find the stop button. There we go. Come on, stop button, load. All right. Have a good day, guys. Bye.